So we're going to take a look at our periodic table. Yours should be colored. I got all the coloring off of here, but I did leave some information that we're going to need, like the S, P, D, and F block and the period numbers. Now the first thing I want to quick emphasize here, these are our group numbers, these numbers across the top. Now what we mean by this, a group, like group 18 would consist of all of these elements in this column. Group 13 would be all of the elements below boron. Group 1 is the first column. So a group or family, they're sometimes called a family, is the column. So that's a column of the periodic table. Now a period or series, those are the two names we'll give the rows of the periodic table. So period 1 would be hydrogen and helium. Period 2 would be lithium and beryllium. Or series 5 would be this row down here. So if you're looking at period 5, group 11, so period 5, group 11, so I go down, that would be silver, Ag. So you should be able to find elements if I tell you which group or which period. Period 3, we've got period 3, group 4. This one doesn't actually exist. There's no element there. So no element. So I want you to do the next two. Pause the video, do the next two. Okay, so hopefully you did them. Series 6, family 2. So series would be the row. Family 2 would be the column, second column, group 2. So that would be barium for this one. And the last one, row 4, group 14. I'd go across till I got to group 14. That would be germanium. Okay, now the parts of the periodic table. If you remember on the periodic table you drew a little we call it the stair step line, a little zigzag line that starts up at boron and it zigzags down to the bottom right. Now the metals are found on the left of the stair step line. So to the left of the stair step line, you may or may not have left them uncolored, depending if you decide to color that side in. I didn't color it in when I did it on the previous video. Those are your metals. They're typically shiny, they're solid at room temperature, and they're good conductors of heat and electricity. There is one metal that is not a solid, that would be mercury, but the rest of them are solid at room temperatures. And depending on what you consider room temperature, gallium would be right on the edge. But for this class, let's just say mercury is the only liquid at room temperature. Gallium is one of those metals you've probably maybe seen videos where if you put like a gallium spoon in your hand, it'll just melt in your hand because your hand is warm enough to melt it. So that's why that one's iffy about the room temp. Anyway, so this includes the alkali metals, alkaline earth metals, and the transition elements. The nonmetals, these are generally gases, or if they are solids, they tend to be brittle and dull looking. So think graphite. If you look at your pencil right now, the pencil lead is actually made out of carbon, which is graphite. So it's just a dull looking solid, and it's brittle, it snaps. They are poor conductors of heat and electricity, typically. They are to the right of the stair step line. So you'll notice that the majority of the periodic table is actually made of metals, because the left-hand side of that stair step line is much bigger than the right-hand side. It's not an even split. So the nonmetals make up that top right corner. Don't forget about hydrogen though. Even though hydrogen's on the far left on the top up by itself, it is a nonmetal. And it is a gas at room temperature. The last one is the metalloids. Now metalloids are right along the stair step line. They're also called semiconductors. They have properties that are very similar to right in between metals and nonmetals. And for the longest time, a lot of chemists and I guess people thought that the metalloids were mostly useless because if you wanted to conduct electricity, you used a metal. If you wanted to not conduct electricity or heat, you used a nonmetal. Why would you ever want to do something that's somewhere in the middle? Well, it turns out it comes in very handy when it comes to making computers and a lot of the electronic devices that we have nowadays. So you hear about Silicon Valley over in California, the San Francisco Bay Area, the whole industry on computer chips and electronics is very much built around the metalloids, especially silicon, which is a metalloid. So there you go. It's right along the stair-step line, except aluminum. You'll notice aluminum is right along the stair-step line too. And if you follow the pattern of all the other metalloids, you'd say, oh, well, aluminum must be a metalloid too. But of course it's not. There's always exceptions, right? So know that aluminum is a metal, not a metalloid. Now some fun facts about the periodic table. The synthetic elements, these are the synthetic elements, number 43, 61, and anything 93 or bigger is synthetic. So what do we mean by synthetic? That means they're human-made. That means they are not found in nature. Synthetic means not natural. So they're made in a lab. There's different ways to make elements. I'm not going to get into it in this class. But what you do need to know is that all of them are radioactive. They are all decomposing. Now, most of them, or a lot of them, are for the most part useless. They don't have many practical uses. One of them, though, that is synthetic is americium. It's actually used in smoke detectors. It gives off a decay product that's charged particles, and it constantly is emitting those inside the smoke detector, and those particles hit a metal plate. As long as they keep hitting that metal plate, that plate will conduct electricity and your smoke detector's happy. But as soon as smoke gets in the room, as smoke gets in your smoke detectors, the smoke is really good at blocking those particles. So then as soon as those particles stop hitting the metal plate in your smoke detector, the electricity stops flowing, and then your smoke detector freaks out and alerts you that there might be a fire. So that's how smoke detectors work. That's also why fire departments, you'll always get advice on how to prevent fires or be safe, fire safe in your home. You have to replace your fire detectors every so often because the americium is decomposing and it will eventually run out. So as that sample in your smoke detector slowly starts to fade, the decaying slows down, your smoke detector might start acting kind of goofy, so you need to replace it. Okay, some other fun facts. There are 90 naturally occurring elements, and we know of 118 at this point. And again, the most recent ones were all synthetic. They've been made. We aren't finding any new natural elements. I wouldn't necessarily rule out the possibility. Anything's possible, but it's more likely that future elements will also be synthetic, not natural. Some history of the periodic table. Now, it's easy to think, oh, we've got a periodic table sitting in our classroom. That periodic table has just always been there, but it has been a work in progress over the years, and it's a very powerful tool in the way that it's been organized. That's really helped advance chemistry. So we don't want to take it for granted. So we've got Mendeleev. He's considered the father of the periodic table. There's a lot of people back in his time, so you can see the years he was alive, that were trying to organize the elements. They thought there was a pattern with them. As they're discovering more, they're like, well, is there patterns to the elements? And they were finding that certain elements behave similarly, so they tried to organize them in a way that made sense. And Mendeleev was obsessive about how he organized them. He had about 60 elements, and he organized them over and over and over again until he was finally happy with it. And there's a lot of people that have done the same thing, but the reason Mendeleev gets a lot of credit for being kind of the father of coming up with the original periodic table is that he did something that other people didn't, and he left spaces. He left spaces in the periodic table where he thought that there would be an element discovered that hadn't yet been discovered. And not only did he leave the blank space saying there will be an element that'll go here when we discover it, he was able to predict the properties that it would have based on his patterns. He organized them by how they reacted and their weights and things like that. So he said, okay, this element, I think it was gallium or germanium he left blank, and he said it'll have this property, this property, and this property. And then when it was discovered, it actually turned out that his predictions were very, very accurate. So that's why he's given the credit as being the first one to really come up with a good organized periodic table. So his periodic table looked something like this, not like what we would expect today or what we see today. But there was one big flaw in his periodic table, and that's that he organized them by their trends and their masses. Now, if you look at your periodic table, the masses of the elements do not necessarily go up every single time. There's a few cases where the next element will actually have a lower mass than the previous one. So Mendeleev actually had those elements backwards because he went from lowest mass to highest mass. And it turns out that Moseley fixed that. They ended up arranging them by their atomic number, Moseley did. And that flipped around the few that Mendeleev had wrong. And so then he's considered the father of the modern periodic table. So that's the difference between Moseley and Mendeleev. Mendeleev organized them by their mass. Moseley organized them by their atomic numbers and solved the few problems that Mendeleev had. So if I ask who's the father of the modern periodic table, you should say Moseley. He also came up with the periodic law, which just says that the physical and chemical properties of an element are a periodic function of their atomic number, which is a mouthful, which just means that the properties of elements repeat every so many elements, basically. And it tends to be about every 8 elements. So every 8th element tends to be very similar to the previous one. And that holds very true, at least for the first 3, well, for periods 2 and 3. Those elements repeat every 8 elements.